Today we're going to do some problems from the University of New South Wales 2020 Integration Bee Qualifiers. This video will be the first part of a series where we'll be doing more questions from the University of New South Wales Integration Bee 2020. So the first question from the qualifiers is, we'd like to find the integral of x with respect to x from 503 to 507. Notice that this function is relatively very simple. We can just apply the exponents rule, as we say, where the integral of a times x to the n relative to x is just equal to a over n plus 1 multiplied by x to the power of n plus 1. And since this is an indefinite integral, we need to add a constant in the end. Now, because we see in our function that the integral is definite, we don't need to add this constant here. We'll just need this, and we can just substitute a is equal to 1 and n is also equal to 1, as we see in the function. So yeah, we would get the integral would be 1/2 of x squared, and as the values are set, we can just plug them in later, and here 1/2 of 507 squared minus 503 squared. Notice how I factored the constants beforehand. This is just to make it easier. Now, why would I do that? Like, what would I be helping with? So we see that this is a difference of squares, 507 squared and 503 squared. So just remember that x squared minus y squared is equal to x plus y multiplied by x minus y. So yeah, we can apply that rule here. It will be 1/2 of x minus y times x plus y, 507 minus 503 and 507 plus 503. That'll just make it a lot easier to evaluate rather than finding 507 squared and 503 squared and then subtracting them both. Yeah, so we'll find that this is 4, this is 1010, and this is 1/2. Don't forget to multiply by the constant, and we would get the answer to be 2020, coincidentally to the year of the paper. Alright, now to problem number 2. In problem number 2, we'd like to find the integral of 3 to the power of ln x with respect to x. Now notice that in calculus, the number e, or the Euler's number, it'll be very important, and it will show up a lot due to its very special property where the derivative of e to the x with respect to x is equal to e to the x, which is equal to the original function. Now, how can we apply it here? So we can apply it by knowing that 3 is just e to the power of ln 3. Now we see that this e has two exponents, ln 3 and ln x. Exponents, we can use the associative property, so we can just switch this ln 3 and ln x, we can just switch places. They can switch places. So it can just be e to the power of ln x multiplied by ln 3. Or we can just put it in parentheses to help us understand it more. So it will be e to the power of ln x, all of that over all of that to the power of ln 3. Now we must remember that e to the power of ln x is nothing but x, and yeah, it'll be x to the power of ln 3. Now we can do the reverse power rule like earlier. So it'll be 1 over 1 plus ln 3 Notice that this is the exponent of the original function multiplied by x to the power of 1 plus ln 3 plus c, because this is an indefinite integral. So yeah, that's our answer. Or you can also put it in an easier logarithmic form. Remember that ln a plus ln b is equal to ln a times b. And we can just assume that the 1 is equal to ln of e. Well, we already know that, so we can just plug that in. It'll be 1 over ln of 3e multiplied by x to the power of ln 3e. So yeah, both of these answers are the same. And off to problem number 3. We'd like to find the integral of the square root of e to the power of x dx. So in this problem, we're going to use a u sub, a variable sub, where a is equal to e to the power of x. Notice that dA, the derivative of a with respect to x, is just e to the power of x, or a, just like I said in the previous problem. E to the x is very common, such that we can find that dx is equal to dA over a. Now we can substitute in a and dA into the original integral. That would be the integral of the square root of a multiplied by 1 over a with respect to a. So we can just work around these exponents. So this is going to be a to the power of 1/2, and this is a to the power of -1. And well, since when we multiply any number with the same base, we will get that their exponents should just add up. Henceforth, this 1/2 minus 1 is -1/2. Because of that, we can just apply the inverse exponents law. 1 over -1/2 plus 1, and yeah, -1/2 plus 1. This will be 1 over 1/2 multiplied by a to the power of 1/2. Don't forget to plus c, because these are indefinite integrals. Now 1 over 1/2 would just be 2, and this so the power of 1/2 would just be the square root of a. Or we can already substitute a is equal to ex to make it easier. So the final answer we will get would be 2 times the square root of e to the x plus c. Now let's do number 4. In problem number 4, we'd like to find the integral of the square root of e to the power of x minus 1 with respect to x. Now at a glimpse, this doesn't seem much different from problem 3. However, this is actually rather different once we do the solution, which we will see later, as it often does happen in integration problems. So first off, we'd like to do some variable substitution, where a is equal to e to the power of x minus 1, such that we will get the derivative of a to x is equal to e to the power of x, which, if you pay attention to the original substitution, is equal to a plus 1. So we'd get that dx is equal to dA over e to the power of x, or is also equal to dA over a plus 1. So we can substitute a and dA to the original problem. We'll get the integral of the square root of a multiplied by 1 over a plus 1 with respect to a. Now we can do another variable substitution, where b is equal to the square root of a, such that the derivative of b with respect to a is 1 over 2 times the square root of a. We can just use the exponent rule here, the power rule. So we would get that dA is equal to 2 times the square root of a dB. Don't forget that the square root of a is equal to b. So it'll be 2b dB. So we can just substitute b and dB to the original problem. So we'd be looking for the integral of b over 1 plus b squared multiplied by 2b dB. Now we can factor this 2 out as it's a constant, and we can multiply this b with the other b, such that we would find 2 times the integral of b squared over b squared plus 1. Now notice we have 2 b squareds here. So how do we separate these two terms to make it a lot easier to calculate? We'll notice that b squared is nothing but b squared plus 1 minus 1. So we can just factor this one out and this one out. Just take them out. And we would get this equal to 1 minus 1 over b squared plus 1. Now dB. Now we can do the integration more easily. So yeah, we just integration of 1 dB, which is equal to b, and this, it's rather special. The integral of 1 over 1 plus x squared dx, that would also be equal to arctangent of x. So this is a very special rule in integration. So yeah, we'd find that this is just equal to 2 multiplied by b minus arctangent of b, all of that plus c, because this is an indefinite integral. Now we can substitute then b is equal to the square root of a here, and we could also substitute in that a is equal to e to the power of x minus 1, and because of that we can also distribute the 2. So it will be 2 times the square root of e to the power of x minus 1 minus 2 times the arctangent of e to the power of x minus 1 plus some constant c. Now going on to problem number 5, we'd like to find the integral of cosine of ln x, or the natural log of x, with respect to x. We're going to do that through integration by parts, where we're going to substitute a is equal to the cosine of ln x, such that the derivative of a with respect to x will be the negative sine of ln x multiplied by 1 over x. Where did this 1 over x come from? This is from the chain rule. Remember, the derivative of the natural log of x with respect to x is equal to 1 over x. So yeah, that's where the 1 over x came from. And we're going to substitute dB is equal to dx. So simply b is equal to x. So we can do this problem here, where the integral of cosine of natural log of x with respect to x would equal to x multiplied by cosine of ln x minus the integral of negative sine of the natural log of x multiplied by 1 over x multiplied by x dx. So we can cancel these x's out, and we can see that these are two negative signs, so we can just make this positive and this one nothing anymore. So we can get that the integral of the cosine of ln x with respect to x is equal to x cosine of ln x plus the integral of the sine of ln x with respect to x. Before moving on, I must remind you that there should be a constant, but for the sake of simplification, I'll just be adding the constants in the end. So we will find an integral that we don't know yet, but we can find here integral of the sine of natural log of x with respect to x. Again, we can do the chain rule, where we let p is equal to sine of natural log of x such that we will get the derivative of p with respect to x as the cosine of natural log of x multiplied by 1 over x. Just like earlier, 1 over x came from the derivative of natural log of x to the chain rule. And we'll get, we'll assume dq is equal to dx, so q is equal to x. Now we can find that the integral of the sine of natural log of x with respect to x is x multiplied by the sine of natural log of x right here minus the cosine of the natural log of x multiplied by 1 over x, like here, multiplied by x dx. These two, they cancel out. So we can find that the integral of sine of natural log of x with respect to x is equal to x multiplied by the sine of the natural log of x minus the integral of the cosine of the natural log of x with respect to x. Notice that this unknown integral, well, we kind of know it here, right here, such that we are able to substitute these, or we can substitute these. Now, because we're trying to look for the integral of cosine of ln x with respect to x, we'll need to substitute the integral of sine of the natural log of x with respect to x, such that we'll get that the integral of the cosine of the natural log of x with respect to x is equal to x multiplied by the cosine of the natural log of x plus x multiplied by the sine of the natural log of x minus the integral of the cosine of the natural log of x with respect to x. Notice that this term is equal to this term, so we can just move it to the other side. And notice that we can also factor out x from both of these equations. So, and notice that there should be plus c as well. Should be an added constant, as it's an indefinite integral, but we, like I said, we're going to do it after this. So we'll find that 2 times the integral of the cosine of the natural log of x is equal to x multiplied by cosine of ln x and the sine of ln x, all of that with a constant added to it. So we'll just divide the entire equation by 2, and we will get that the cosine, the integral of the cosine of the natural log of x with respect to x is just x over 2 multiplied by the cosine of the natural log of x plus the sine of the natural log of x plus a constant c. Now next, let's go to problem number 6. In problem number 6, we're asked to find the integral of e to the power of 2x over the square root of 1 minus e to the power of 4x dx. Okay. To do this, let's do some variable substitution. Or we can just simplify the equation first. Remember that through the rules of exponents, e to the power of 4x is nothing but e to the power of 2x, just like the one above, squared. Now we can do the variable substitution as I stated earlier. Assume that e to the power of 2x is equal to a, such that the derivative of a with respect to x is just 2 times e to the power of 2x. Notice that this is also a, so it will be 2a. So in terms of dx, dA is equal to 2a dx, or dx is equal to dA over 2a. Now we can substitute the a and dA to the original problem. We'll find that we're looking for the integral of a over square root of 1 minus a squared multiplied by 1 over 2a with respect to a. Now these two a's, they can cancel out, and this 2 is a constant, so we can just move it to the front. So in the end, we will get that we're looking for the 1/2 of the integral of 1 over the square root of 1 minus a squared dA. This is a rather special function, as I said earlier, as you have seen earlier in the video. Now, what is this special function? It's just the derivative of the arcsine of a with respect to a. Now, how do I prove it? Well, let's just assume v is equal to the arcsine of a, and we're looking for the derivative of b with respect to a, which is also equal to the derivative of arcsine of a with respect to a. Now, you can just find that the sine of v is equal to a. Now we can do some we can derive all of these with respect to a. So sine b with respect to a is equal to the derivative of a with respect to a is equal to 1. Notice that it's hard to do it like this, so let's just do it by the chain rule. The derivative of sine b with respect to b multiplied by the derivative of b with respect to a is equal to 1. Notice that the derivative of sine b with respect to b is nothing but cosine b multiplied by the derivative of b with respect to a is equal to 1, such that the derivative of b over the with respect to a is equal to 1 over cosine b, or if you remember, sine squared b plus cosine squared b is equal to 1. So you get that cosine squared b is equal to 1 minus sine squared b, or cosine b, is equal to the square root of 1 over sine squared b. Now we can substitute this sine b as a, so it will be equal to the square root of 1 minus a squared, such that the derivative of arcsine of a with respect to a is equal to 1 over square root of 1 minus a squared. Right, so we've proven that, and we see that this dA we can just cancel each other out. So yeah, we'll get 1/2 of the integral with respect to arcsine of a. So it will be 1/2 of arcsine of a plus c, and we can substitute a is equal to 2x, so we'll get it will be equal to 1/2 of the arcsine of e to the power of 2x plus c. And now to the last problem in the video, problem number 7. So in problem number 7, we'd like to find the integral of 4x cos x over x squared minus the sine of the absolute value of x plus the cosine of the absolute value of x with respect to x from negative 7 pi over 4 to 7 pi over 4. One of the first things that we can notice is that this bottom limit and the top limit, their absolute values are the same. However, they are from different sides of the number line, meaning one is negative and the other is positive. In these types of problems, what often happens is an analysis of the function, the original function, whether it is an odd function or an even function. Now, what is an odd function and an even function? We will get to it in this problem. So one of the easy ways to test if a function is odd or even is to test the value of the function at a certain number. We assume a and its negative value, or it's the value of the function at negative a. Now let's do that. So let's take the original function here, 4x cosine of x over x squared minus the sine of the absolute value of x plus the cosine of the absolute value of x. Now we'll try to find the value of the function at a certain value. For example, for x is equal to a and a is greater than 0. We can substitute in a for all the x's here in the original function here. So this a goes here, 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 and here. Now notice that the absolute value of a, because a is positive, is equal to a. So yeah, we can just manipulate that here and here, and we would find that fa is equal to 4a cosine of a divided by a squared minus sine a plus cos a. Alright. Now, how about 4x is equal to negative a, and a is greater than 0. We assume this a is equal to that a. Okay, we'll get that the value of the function at x is equal to negative a. Well, we'll just substitute negative a for all the x values. So we'll substitute it here, 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 here. Alright. Now, one thing we should notice from trigonometry here is that cosine of negative a is equal to cosine of a, and because this is an even number for the exponent, the negatives cancel out, so it'll just be a squared. The absolute value of negative a is also equal to a, such that we can do the same here. So the only difference really is here in this place. So we'll get that the value of the function at x is equal to negative a is equal to negative 4a cosine of a over a squared minus the sine of a plus cosine of a. Or we can see from this in these two that f of negative a is equal to negative fa. Now, what does this mean? This means that fx is an odd function. Alright. Now, for odd functions, there's a rule here for any odd function where it's negative y and y, just like this problem, negative 7 pi over 4 and 7 pi over 4 of the function with respect to x is equal to 0, such that we can just substitute in y is equal to 7 pi over 4 and fx is equal to this function here for x cos x over x squared minus this sine of the absolute value of x plus the cosine of the absolute value of x, which in the end will equal to 0. So yeah, these are all the problems in this video. I hope you enjoyed this video. Thank you.